Hi everybody, it's Dr. Nigro with the Chem Calculations Screencast. This one looking at how to determine the standard cell potential for a particular electrochemical cell. All right, we represent that standard cell potential with the symbol E with a little circle up top and subscript cell. All right, the little circle that's a superscript here just tells us we're under standard conditions, so STP conditions. All right. Generally speaking, when I want to calculate the cell potential, I need to look at the sum of the potential of the reduction reaction plus the the potential of the oxidation reaction. I need to add those two together and see what that cell potential is. If your cell is spontaneous, right, in other words, a voltaic cell, then this value should be positive, right? If instead you have a non-spontaneous, right, which is an electrolytic cell, then we're going to have a negative sign here. Or remember, the electrolytic cell does require outside energy to make that flow because that reaction is not spontaneous. It does not want to flow under standard conditions. All right. So where do I find the reduction and oxidation potentials? Well, you're going to have a standard reduction potential sheet. Table. All right. So in other words, you're going to have a table full of reduction potentials. All right. Which is great for the reductions, but what about the oxidations? All right. All right, if you have an oxidation half reaction, you need to change the sign of that reduction potential. All right, you do not need to do anything else to it. If you take two half reactions and you need to double one or triple one, it has no effect on our reduction or oxidation potential, because once those potentials are flowing, it's just looking at the buildup of electrons around the voltmeter. It doesn't look at each individual reaction. It looks like at a multitude at one time. All right, so do not change the number, only the sign. Okay, now we are going to be dealing with voltaic cells. All right, so we want them all to be spontaneous. So we need that cell potential to be positive. In those cases, the more active metal should be our reduction. Oh, sorry, I just said that backwards. Should be the oxidation. Sorry about that. All right, the more active metal wants to give up electrons, that means it's being oxidized. So this is going to be our oxidation half reaction. It just helps you, instead of having to go through the different options, the different ways to put the cell together, it gives you a starting point. It's just a good rule of habit. All right, so let's look down here at our examples. For each of these, we're going to identify the anode and the cathode and then calculate the standard cell potential. All right, so we have a voltaic cell, so that means I need E cell to be positive, consisting of a nickel electrode in contact with a solution of nickel ions and a silver electrode in contact with a solution of silver ions. All right, so I'm going to go look at my activity series and I'm going to see that nickel is more active than silver. All right, so that tells me that nickel is my oxidation. All right, so I'm going to come over to my space over on the left, and I'm going to write out my two half reactions. I have nickel solid forming nickel plus 2 ions plus 2 electrons, right? And I'm going to go look on my reduction potential sheet to find that cell potential. Oops. All right, and if I look, it has a reduction potential listed as negative 0.26. but I have the oxidation here, so it's going to be a positive 0.26 volts. All right, now I'm going to do my reduction. So if nickel is being oxidized, the silver ions must be reduced. So Ag plus yields Ag solid. All right, 2 electrons are transferring between these, so I'm going to have 2 ions and 2 metals. All right, I go check my reduction table, and I see that the reduction potential for silver ions to silver is a positive 0.80 volts. Now, I do not touch that value. I don't change the sign because it's a reduction potential, all right? And I don't change the number even though I doubled my half reaction. My cell potential is the sum of these two numbers. So I add them up, and I have a positive 1.06 volts. Right? That positive sign tells me that this is a spontaneous cell, which is what a voltaic cell is. All right, let's try another one. This time, a voltaic cell. So again, we need the cell potential to be positive, consisting of an aluminum electrode in contact with a solution of aluminum plus 3 ions, and a chromium electrode in contact with a solution of chromium plus 3 ions. All right, so again, I go check my activity series and I see that aluminum is more active. All right, so that's going to be my oxidation half reaction. So I have aluminum metal forming aluminum plus 3 ions and releasing 3 electrons. I go check my reduction potentials, and I find aluminum is negative 1.66 volts if it were a reduction, but here we're using it as an oxidation, so positive 1.66 volts. All right. While aluminum is being oxidized, chromium is being reduced. All right. So we have Cr plus 3 ions, and we're forming chromium metal, and we're using those 3 electrons from the aluminum oxidation to make that happen. So I go check my reduction potentials again, and this time I see that the reduction potential for chromium is negative 0.74 volts. Right, again, I don't change anything about that value. It's a reduction. It just stays as is. And so my cell potential is the sum of those, and I find that it's 0.92 volts. All right, it's positive, which is spontaneous, which is what a voltaic cell should be. All right, so again, these aren't that difficult if you keep in mind that the more active metal should be the oxidation. If you put your cell together and you find that your cell potential is negative, then you've flipped your 2 half reactions. You need to go back, rewrite them, change the signs of your 2 potentials, and then try again. I just find if you start out by using the more active metal as the oxidation, you're going to be correct 99.99% of the time.